Okay, folks, welcome to the next section in Chapter 6, where we're going to continue looking at trigonometry equations. So we're going to look at another level of these. Specifically, we're going to look at equations with half angles and multiple angles. So let's just get right in. We're going to do this similarly as we've done in the last section, where we're kind of looking at our knowledge and learning and experience from algebra and then combining it with our new knowledge in trig. All right, so and then there are some caveats in here about how the periods will change and the intervals will change, okay, based upon the angle. So we're going to use some of the knowledge that we gained in graphing and how that different multiples, etc., changed the value of the function. All right, so let's look at this first problem. Solve 2 sine x over 2 equals 1. And first we're looking just over the interval from 0 to 2 pi, so we're in radians. And then B, we're looking for all possible solutions. So then we're just going to add the period to find all the coterminal angles for each of our solutions. Okay? Remember that this interval that's given here is for the variable, and in this problem it's x, okay? So we're saying that x is between 0 and 2 pi, not x over 2. So that's kind of the first kind of thought that you have to be mindful of when you're doing these multiples and half angles, okay? That when you're given an interval for an equation, it's always for the variable x or theta, not for some multiple of that, okay? So if x is between 0 and 2 pi, notice that for A, we're looking for solutions for x over 2, which are between 0 and pi, because we just divide each of these interval endpoints by 2. All right, so now we're ready to solve the problem. 2 sine x over 2 equals 1 is equivalent. If we divide both sides by 2, we get sine x over 2 equals 1/2. Well, the sine of pi over 6 is equal to 1/2. We know this from our triangles and our known angles before. And this will be our reference angle. Since x over 2 is between 0 and pi, notice this is in quadrant 1 and quadrant 2. So in quadrant 1, the reference angle is the angle, and in quadrant 2, the reference angle of pi over 6 is equivalent to 5 pi over 6, which is, of course, pi minus pi over 6. All right? But notice this was the solution for an angle. The sine of pi over 6 equals 1/2. So we have to figure out what x is. And so x over 2 equals pi over 6, or x over 2 equals 5 pi over 6 for the solution, the second quadrant. Of course, this gives us x multiplying both sides of this first equation by 2. We get x equals pi over 3, 2 pi over 6, or pi over 3. And then, of course, here, multiplying both sides of the equation by 2 to just get x, we get x equals 10 pi over 6, or 5 pi over 3. So our solution set for A is pi over 3 and 5 pi over 3. All right. Now for B, we have to find all solutions. And typically... Hello, Moto. Sorry about that, guys. Got an airplane and my phone ringing. Remember that when we're trying to find all solutions, we add the period. So normally sine has a period of 2 pi. So normally we would just add 2 pi to this. So we'd have all solutions would be pi over 3 plus 2n pi and 5 pi over 3 plus 2n pi. But remember back when we were graphing that if we have a multiplier in front of the angle, which we called b, remember that was the multiplier, so the sine of bx, you might remember that from when we were graphing, that we find the period for sine by dividing 2 pi by that multiplier, okay? And so here, sine of x over 2 is the same thing as the sine of 1/2 x, and thus b equals 1/2. So if we divide 2 pi by 1/2, that's the same as multiplying it by 2. And so in this problem, we're actually looking for a solution that has a period of 4 pi, okay? This has a period of 4 pi. So instead of adding 2 pi n to each of these solutions, notice we are adding 4 pi n because of the multiplier on the angle of 1/2. Again, hopefully this is a little bit of refreshing knowledge from back when we were doing graphing and trying to figure out new periods based upon multipliers of angles. Okay, so when you're doing these half angles or multiple angles, it affects the period. It obviously affects the answers, as we saw, because we solved the original sign for x over 2, but we needed to find out what x equals after that. All right, so let's try another problem. Solve cosine 2x equals cosine x over the interval 0 to pi. So this is really like having two different variables, since we have two different arguments, okay? And so this is a challenging thing as well. So we have cosine 2x equals cosine x. Well, if you remember, we have an identity here for the cosine of 2x, and this is what we want to do. We want to get rid of the argument 2x so that every cosine in here is of just the argument x. And so we've used the double angle identity for cosine, where the cosine of 2x equals 2 cosine squared x minus 1. Now we can solve this like we did in the last section, because now we're just dealing with the same, technically the same variable, cosine x and cosine x, okay? We can see this is a quadratic, so we're going to set it equal to 0. You might remember in the last section I talked about changing out, if you can't see how to factor this, do a substitution where cosine equals x, then you'd have 2x squared minus x plus 1, and that might help you to figure out the factors better and then just substitute it in. I'm not going to go through that step again. I did that in section 6.2 where I showed you how to use x substitutions so it looks more like algebra and you don't get kind of, you know, in the weeds mentally by looking at this quadratic with a trigonometry function. So this does factor into 2 cosine x plus 1 and cosine x minus 1. All right. Another thing you can always do too is just use the quadratic formula. In this case, a would be 1, b would be negative 1, and c would be positive 1. I don't know if I said that right. A would be 2, b would be negative 1, and c would be positive 1. Since we have factored it equal to 0, we set each of those factors equal to 0 and solve. So on the left, we get cosine x, first by subtracting 1. 2 cosine x equals negative 1. Divide by 2, so we get cosine x equals negative 1/2. This again is a known angle. This would be, cosine is the x value, so this is in quadrant 3 and quadrant 4. So we get 2 pi over 3. And that's not right. Cosine is negative in quadrant 2 and quadrant 3. Cosine is the x value, remember? So it's quadrant 2 and quadrant 3. So we get x equals 2 pi over 3 because the reference angle is pi over 3. And then in quadrant, that's quadrant 2, and in quadrant 3 we get x equals 4 pi over 3. To solve the other one, we get cosine x equals 1 by adding 1 to both sides. And of course this only happens when x equals 0. Okay, so our solution set here are those three values, 0, 2 pi over 3, and 4 pi over 3. Let's look at another problem. For sine theta, cosine theta equals the square root of 3 over the interval 0 to 360. Okay, so now we're dealing with degrees, so if we have to use our calculator, make sure we're in degree mode. All right. Again, we have a problem here because we have sine theta and cosine theta. And so this is like having two different variables in here, and we can't solve for two different variables with only one equation. So we have to figure out some way to rewrite this equation so it's only in terms of one trig function. And last time we had two cosines, but they had different arguments, 2 theta and theta. This time we have the same argument, but two different trig functions. So we have to figure out a way to rewrite this using, our knowledge about relationships and properties of the trig functions. It's not very easy to rewrite sine and cosine in terms of anything that's going to get rid of one of them. So when we're kind of stuck like that, if this was tangent or something, that might help us out. But when we're stuck, a good idea is to go and review your identities. I call it go fish. Do you have anything that looks like 4 sine cosine, right? And to look through your identities, you might see something that looks like this. 2 sine theta cosine theta is equal to the sine of 2 theta. Well, we don't have that exactly, but we can manipulate this by factoring out a 2. And so we have 2 times 2 sine theta cosine theta, and now we can do a substitution, which gives us just one trig function, which is really one kind of one variable, if you will. Okay, so since 2 sine theta cosine theta equals sine 2 theta, we multiply that by 2, and now we have a simplified equation which we can solve, divide both sides by 2, and so we get the sine of 2 theta equals the square root of 3 over 2. Again, this is a known angle. This is from the triangle 30, 60, 90, and specifically, it's the reference angle of 60. Since sine is the y value, sine is positive in quadrants 1 and 2, we want to make note of that as well. Okay, so in quadrant 1, sorry, I moved on. So again, because we've now changed our argument from singly theta to double theta, we also have to look at the interval. If theta goes between 0 and 360, then 2 theta, we're going to have to multiply both of these sides, is going to go between 0 and 720. So that means we're going to get a quarter 1 and a quarter 2 in the first revolution, and a quadrant 1, I said quarter, sorry, quadrant 1 and quadrant 2 answers in the second revolution. Okay, in quadrant 1 we simply have 60 degrees, in quadrant 2 we have 120, and when we're looking for the second revolution we simply add 360 to each of these because we're looking for coterminals on the next revolution around since we doubled this, and so we get 420 and 480. And then just to make this more complicated, remember when we're solving this equation, we're solving for theta, not 2 theta, so we have to divide each of those answers by 2. And so our final solution is 30, 60, 210, and 240 for this problem. Okay? So you can see there's a little bit of complications in here. We first had to play go fish and figure out something that looked like this so we could do a substitution. When we did, we changed our argument from a single variable theta to a multiple of that, and so that affected not only our interval, it affected our answers, and then of course we had to come back and make sure that we were answering for theta, not 2 theta. So there's some steps in here that you really have to pay attention to for each of these. All right. Well, I don't remember that being on there. So we have that same problem, but let's solve it for all solutions. Remember, we solved this for 2 theta, so we need to use this to find all the solutions. All angles 2 theta that are solutions of the equation are found by adding integer multiples of 360 to the basic solution angles 60 and 120, okay? So if we wanted to find all answers for 2 theta, we'd have 60 plus 360n, or 120 plus 360n. But again, that's giving us all solutions for 2 theta. And so in order to find this all solutions for theta, we simply divide those numbers by 2. Okay, so we get 30 plus 180 and 60 plus 180. Okay. So this is our, when we're writing this, of course, we write it as 30 plus 180 degrees n and 60 plus 180 n, so that we're doing all multiples as we continue to circulate around revolutions, if you will, each 2 pi. Okay, let's look at another problem. Solve tangent of 3x plus the secant of 3x equals 2. Again, we have a problem here. We have a couple challenges. One, we have multiple angles instead of a single variable, not just tangent of x. And then we have two variables in terms of our trig function. We have tangent and secant. Well, we know that tangent and secant, there's a relationship between them, one of the Pythagorean principles or rules or identities. And so we can use that to express everything in terms of secant. And so that's what we're going to do in this problem. Okay? So we get tangent plus secant 3x equals 2. We want to isolate the tangent x so that we can rewrite it as secant. And remember, the relationship that's between tangent and secant is a squared relationship. So we're going to square both sides. Tangent squared 3x equals 2 minus secant 3x squared. And of course, if we square the right side, we just did that to kind of so we could see that and not do too many steps at once. Remember, we're foiling this. This is not 4 minus secant squared. You've got to get that middle term in there by using the FOIL process. Okay? And of course, tangent squared equals secant squared minus 1. So tangent squared 3x is the same as secant squared 3x minus 1. And now we can see we can isolate secant on its side. If we subtract secant squared from both sides, notice the secant squareds disappear. And we get 4 secant 3x equals 5. If we take the secant, negative 4 secant x to the left side of the equation by adding it to both sides, and add 1 to both sides. And so we get this simple equation. Divide both sides by 4, and we get secant 3x equals 5/4. Since we're going to be looking for this is not a known angle. This is not a known angle, so we don't have an exact measurement. And so since we're going to be using our calculator to figure out what the angle is using the inverse trig function, it's easier if we convert this into cosine. Okay, so we get cosine 3x equals 4/5. Okay, right, because cosine and secant are inverses. So we need to figure out what angle gives us the measure of 4/5 with the cosine function. All right. So let's look at that. So we're looking, again, we have a multiple angle. Cosine is over 2 pi. So we have to multiply each of those by 3 because that's what x is between 0 and 2 pi. So 3x is between 0 and 6 pi. Thus, we can use our calculator to do arc cosine 4/5. And since cosine is positive, this answer is positive. We know we're dealing with answers in quadrant 1 and 4. So 3x in quadrant 1 is 0.6435. That gives us our reference angle. We can subtract that from 2 pi to get our quadrant 4. So our first two answers are quadrant 1 and quadrant 4. And then each of these subsequent answers are found by simply adding 2 pi. So we get 0.6435 plus 2 pi gives us that coterminal in the second revolution. Adding 2 pi to this gives us that coterminal quadrant 1 in the third revolution. We do the same thing with the second angle. We found this angle by using our reference angle. 2 pi minus 0.6435 gives us this, our quadrant 4 answer. Then we add 2 pi to that to get the coterminal in the second revolution. Add 2 pi to this to get the angle, the coterminal in the third revolution. And if that wasn't enough answers, of course, that's the solutions for 3x. To find the actual answer for x, we have to divide each of those numbers by 3. I know, you're frickin' hating me by now. And then, just when you thought it was safe, right, we have to check all the answers. Why? Because we squared both sides of the equation. And when you square both sides, negatives become positive and become what we call false positives and bad solutions, okay? So we have to go through and check each of these answers, and there's all the calculations on your calculator. You can look at them. I am not going to walk through them, okay? But when we do that, we see that there are only 3 solutions, and these are all the solutions in the first quadrant. 1, 2, 3. All right. So I know that was a mouthful. It was a lot to digest. Hopefully I explained that well. And again, you can listen to it again.